All right, so this is lecture 5, and we are continuing with KarnaughMAPs. Actually, we have covered the basics of KarnaughMAPs, and let me just say it again. Even though the examples that so far I've been starting with the truth table to show that, okay, here is the functionality in terms of truth table, then we turn it into KarnaughMAP. But now once you understand the main concepts of KarnaughMAPs, I probably won't need to just show you the truth table for every example that I'm doing. I will just show you a KarnaughMAP and then highlight on the areas specific to the KarnaughMAP. So this is what we have so far. We have 2 variable maps and 3 variable maps. 2 variable maps are easy, and 3 variable maps something like this, and they are numbered A, B, C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. The reason we do this is for the purpose of adjacency. Okay, so the 2 adjacent boxes in our KarnaughMAP, they also have terms that are Boolean adjacent. Okay, we have talked about those. And then we have these numbers that help us go from truth table to KarnaughMAP. 0, 1, 2, 3. Going to the first column, skip it, come back to it, 4, 5, 6, 7. And we have already done several examples, and some of the examples have illustrated the way adjacencies work. Let me do one example here of the truth table again, and of the KarnaughMAP, again without having to go through necessarily the truth table. So the question is this: I have a 1 here, I have a 1 here, I have a 1 here. Now, if you go back to our definitions, these are min terms of the function, okay? And let's say that I have a 1 here. And I'm trying to get the equivalent of this function, or I'm trying to write the minimal realization of this function. When I say minimal realization, it means that the Boolean expression, the 2-level Boolean expression that will result in fewer gates and fewer transistors when implemented. We have already talked about the mapping of the adjacent ones, okay? Here, I have 2 adjacent ones that I can map. I have these 2 adjacent ones that I can map. Okay? And I have another 2 adjacent ones that I can map, which are, these 2. Okay. And then I have another 2 adjacent ones that I can map that are, one is on this side and one is on this side. Right? Remember I said about the KarnaughMAP that if you look back, behind the KarnaughMAP, it looks like a circular KarnaughMAP, okay, or a cylindrical KarnaughMAP. So the back of it, we see these 2 are adjacent. The question is, do I need all 3 of them? Okay, and if not, which one is it that I do not need? And also the question is, this is a small map, and I can probably realize soon that there is this light blue one that I do not need. But then what kind of procedure can I come up with for understanding or knowing that the blue, light blue one is the one that will not be needed. All right, this is what I'm going to do. I'm going to start more definitions here. Okay, I'm going to write implicants. An implicant of the function is any product term that if it becomes 1, the function becomes 1. Okay? A product that when it becomes 1, the function becomes 1. All right. What are the implicants here? Well, the implicants here are easy to see, actually. This is an implicant, this yellow one. This is an implicant. This is an implicant. This is an implicant, right? Because each one of them corresponds to a product term. So is the combination of these two yellow ones, that's an implicant. The combination of these two, that's also an implicant. The combination of these two is also an implicant. Okay, so I have 1, 2, 3, 4, 5, 6, 7 implicants for this function. Because there are 7 product terms. One of them being, let's say, ECE. That if it becomes 1, the function becomes 1. Okay? So let's write down all the implicants of the function. A, B bar, C bar, that's an implicant. A, B, C is an implicant. A, B bar, C is an implicant. A, B bar, C bar is an implicant. How about B bar, C bar? That is an implicant. How about AB? That is an implicant. How about AB bar? Also, that is an implicant. Okay? So there are 7 implicants here. Because each one of these product terms, if it becomes 1, the function becomes 1. But then there are also prime implicants. Prime implicants are those implicants that are not completely covered by any other implicant but themselves. Okay? So, is A, B bar, C bar a prime implicant? Let's look. A, B bar, C bar. A, B bar, C bar. Is this corner spot of the KarnaughMAP? A, B bar, right. That's the one above it. So this is A, B bar, C bar. It is definitely an implicant. But then, look, that is already completely covered by 2 other implicants. And therefore, that is not a prime implicant. Okay? So I can say the same exact thing about this one, this one, this one, and this one for now. So let's look. Is B bar, C bar, let's identify each one of them. B bar, C bar, which is this green one. Is this a prime implicant? Well, this is not entirely or completely covered by any other implicand, just except itself. So yes, B bar C bar is a prime implicand. Is AB a prime implicand? Well, AB is this one here, and then I can say the same exact thing about that. Okay? It's not completely covered by any other implicand except itself, and therefore AB is also a prime implicand. Do I have any other prime implicand? Let's look at this one. This is A B bar. Is this a prime implicand? What's my sentence? My sentence is a prime implicand is an implicand that is not entirely covered by any other implicand. Well, this qualifies as a prime implicand. Okay? It is true that one of its mean terms is covered by B bar C bar. One of its mean terms is covered by A, B, that are implicand, but it is not entirely, completely covered by any other implicand, and therefore, yes, indeed, A, B bar is a prime implicand. Let's go further with our definitions. Now I'm defining essential prime implicants. Essential prime implicants are those prime implicants that have at least a mean term not covered by any other prime implicant. Okay? Let's look at AB. AB has this mean term that qualifies it as an essential prime implicant. B bar C bar is a prime implicant that has this mean term that qualifies it as an essential prime implicant. How about the light blue one? The light blue one does not qualify as an essential prime implicant, and therefore the only essentials are AB and B bar C bar. In coming up with minimal realization of a function, I start, but this is the procedure now. Start with PIs, start with essential PIs, include all essential PIs, okay, blindly, don't ask any questions, just write down all the essential prime implicants, okay, so my function is AB ORed with BC, B bar C bar. Okay, include all the product terms, OR them together, ORed with, I don't know, maybe. And then look to see if the essential prime implicants that you have already written cover all of the mean terms of the function. Let's check. I'm sorry, this is AB. AB AB covers this and this. B bar C bar covers this and this. And I made a mistake even when writing prime implicants, right? So prime implicance is B bar C bar, which is, oh, I see, this is AC. This is AC, and this is AC. Okay, thanks. So AC is a prime implicant, and B bar C bar is a prime implicant. These prime implicants completely cover all the minterms of the function. So the procedure goes like this. Start with essential prime implicants and include all the essential prime implicants. Then check to see if you are covering all the minterms. If you are covering all the minterms, you are fine. If you are not covering all the minterms, if all minterms are not covered, then you go and start choosing your prime implicants. Okay? Choose those prime implicants that cover the most number of uncovered minterms. Okay? So that's the procedure. Now, for this particular function, as soon as you wrote all your essential prime implicants, you are all set. Okay? And since you have written all your essential prime implicants, and then you don't need to go and look at the prime implicants, you are sure that this implementation of the function is unique. Okay, because you didn't have to go and start choosing. Okay, I'm going to do another example here that is going to be somewhat different from this, and you go into choosing. All right. All right, let's do this example here. Sometimes these examples are hard to come up with. Here is another example. I'm going to go through the same procedure I showed before to do the minimal realization for this function. Okay, and if I want to write the function of ABC as sum of its minterms is minterm number 1, right? Minterm number 3, minterm number 4, minterm number 6, and 7, right? I could do a KarnaughMAP, I could do a truth table, and these numbers that I'm writing are the row numbers corresponding to the decimal equivalent of the binary numbers in the rows. So actually, this is the one that I was using for, I was using the yellow numbers. This is 0, 1, 2, 3, 4, 5, 6, 7. All right? So that's beside the point. I'm just showing that to show a different representation of the function. But what I'm showing here is I'm trying to come up with the minimal realization of this function. For minimal realization, I have to first identify let's not worry about implicants. Let's start with prime implicants. This is a prime implicant. This is a prime implicant. No. That's another prime implicant, right? Because this is not entirely covered by any other implicant. This is also a prime implicant, this green one. Okay, so I'm going to write these. AB is a prime implicant. BC is a prime implicant. A bar C is a prime implicant. And then there's another prime implicant, which is this one over here. Okay, which is a C bar. So I have 4 prime implicants here. These are the prime implicants. What I have to do is to choose the minimal number of these essential prime implicants to cover the function. Now what I have to do is to identify the essential prime implicants. I go in there and say that, okay, this red one, because of this one over here, which is not covered by any other prime implicant, that is an essential. So A bar C is essential. The orange one is not essential, right? The blue one is essential because of this one over here, so this is also essential. So my EPIs are A bar C, A C bar. Okay, the minimal realization of my function is A bar C or A C bar for now. But now let's go in there and find what mean terms I'm covering with including these 2 essential prime implicants. A bar C covers this one and this one. A C bar covers this one and this one. Do I have all my mean terms covered? No, I do not. Okay, and the mean term here is left uncovered. So what do? I go to the step shown over here down on the right hand side, saying that if not all the mean terms are covered, choose from the mean prime implicants that do cover that. Then I say, well, I have a green one and I have an orange one. Fortunately, both of them cover it. And therefore, I have either the orange one, which is BC, or the blue one, which is AC bar, to include. The thing is, after including either one of these, my function is going to be covered. What it means is that my function can be either this or this. And my function is not unique, which is fine. What it means is that the minimal realization, there are 2 alternative forms for the minimal realization of my function. Okay. There are more examples we can do. Let me do one more example here, and I'm just coming up with one example with what it covers, or how it's gonna be as far as using the essentials and all that. I don't know, but let's do it anyway. 0, 0, 0, 1, 1, 1, 1, 0. I have this. And let's say a 1 here. One, two, three, four, 5, 6, 7, 8, 9, 10. I'm counting 11 implicants. 11 implicants. Look. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? Because each one of these is a product term that if it becomes 1, the whole function becomes 1. For example, this big one is C. And if C becomes 1, my function becomes 1. Of all of these implicants, let's find the prime implicants. All right? This is not a prime implicant, the one I just removed, because there is already a prime implicant or an implicant C, that covers that entirely. This one, just see the one I'm erasing, this is not a prime implicant because of the same exact reason, because C covers that too. This is not a prime implicant because C covers that too. This is not a prime implicant because C covers that too. Okay? This is the other half of it. None of these 4 are prime implicants because C covers them all, including this. The little one up there, on the upper right-hand corner, is also covered by A, B bar, and therefore this is not a prime implicant either. So the only 2 prime implicants that I have is C and A bar B. Now I'm writing the minimal realization. For the minimal realization, I say f of A, B, C is included. Okay, now I have to find out the essential prime implicants. A bar B is essential because of this 1. C is essential because of this one, or this one, or this one. Because no other prime implicants covers neither one of these, or any of these min terms. And therefore my function becomes A bar B or C. Implementation of this function is A, B, C. This is A bar, B, C. Okay, I have A bar B. W or F or whatever. And if I want to turn this into all NAND gates, I can easily do this, 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 and C bar. Which implies, or it is equivalent to the use of De Morgan's theorem. I mean, if I had written this like this, A bar B or C, I break the upper or the lower bar, this becomes A bar B, ended with C bar. Okay, which is what I have down here. All right, as far as 3-variable KarnaughMAPs, we have covered everything. Next is other questions. Okay. Should I give you something as an exercise? Let's say an in-class exercise, huh? Okay, that's easy. My function ABC is defined as sum of mean terms 0, 4, 6, 7. Okay? And I'm trying to minimize that. The easiest way to do a KarnaughMAP. ABC, and therefore this is a 3-variable function. There is a 1 in location 0, or there is a min term in location 0. There is a min term in location 4. Let's count. See, the counting goes like this. 0, 1, 2, 3, 4, 5, 6, and 7. And therefore, 4, 6, and 7. These are the min terms of the function. All right, let's find the implicants, prime implicants, and really we don't need to find the implicants because there are too many of them, but then we can directly go to prime implicants. The prime implicants of the function are the following. This is a prime implicant. This is a prime implicant. And this is a prime implicant, half of it on the right side, half of it on the left side. Right? Now let's find the essential prime implicants. Anyone who covers this is essential, because there is at least a 1 or a min term not covered by anybody else. Whoever covers this is essential because of the one that I just put an asterisk next to. All right, with all of this, now let's write the implementation of my function. The green one is going to be there, and therefore it's going to be B bar, C bar. The orange one is going to be there, which is A, B. Now let's see if we are covering all the min terms of the function. B bar C bar covers this and this. AB covers this and this. Well, I'm glad to say that all the min terms are covered, and therefore this is the minimal realization of the function. Notice that I still have one prime implicant which I'm not using, which is fine. Okay? All right, this is another example. Let's move on to the next step, and let's do 4 variable Karnaugh maps. I start with this. Obviously, it has to be something like this, right? I go AB, CD, 0, 0, 0, 1. I've already decided 1, 1 goes here, 1, 0. Okay, now let's number the columns. 0, 0, 0, 1. For the same exact reason that I put 1, 1 on the third column, I'm going to put 1, 1 on the third row. Okay, on the third row. And then 1, 0. This way, if I have a mean term here, a mean term here, okay, the upper one is A bar, B, C bar, D. The lower one is A bar, B, C, D. Right? They are Boolean adjacent. Look, because they are only different in C, that means C is going to be dropped, which is the same thing that I'm going to get from here. Okay? And if I write that green term directly from the Karnaugh map, it comes out as A bar, B, D, no C. And therefore, Boolean adjacency and physical adjacency do correspond. I'm going to do something. I'm going to put a 1 here, a 1 here. Let's write down the adjacencies, or the Boolean expressions. The one on the left is A bar, B bar, C bar, D. The one on the right is A, B bar, C bar, D. Tell me, Boolean-wise, are these two product terms adjacent? Yes, they are. How about physically, those two mean terms, are they adjacent? Well, if we look at the Karnaugh map, like a cylindrical Karnaugh map, yes, we go to the back of the screen and we find that these two ones are sitting next to each other, and then I say, well, if I want to map these, I map these two. And if I map these two, because A is not the same in both maps, A drops, and therefore I come up with B bar, C bar, D. I can say exact same thing now for a 1 up here and a 1 down here. Okay? The one up there is A bar, B bar, C bar, D bar. The one down there is A bar, B bar, C, D bar. They are only different in C, and therefore I could map these two like that together, dropping C. A bar B, thanks. A bar B, C bar D bar, right, thanks. Okay, let's do something else. I'm going to put a 1 here, a 1 here. Actually, with the Karnaugh map interpretation as it being spherical, oh, So far I only said cylindrical. Cylindrical from right and left, cylindrical from up and down. So what it is look at it as spherical. Okay, so it is a KarnaughMAP that actually, if you go to the back of the screen, I used to say board, but now we are doing a screen these days. If you go back to the back of the screen, you actually find this one, this one, this one, and this one to be sitting next to each other exactly like these four here. Right? Visualize this as a sphere, and then go back, you see these four, okay? The four on the corner, they are sitting next to each other in a square. And therefore, I can map those as, let me just take some of these out. This, 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 and this. Okay. Is A the same in all of these? No. Is B the same in all of these? Yes. So this becomes B bar. Is let me erase some of these because I want to treat this function as a new function. What else? What else is the same in all of these four? But it is D bar. So this is it. Okay. And if I all right, let's do another function. How about this? So this one is C bar D. This one is CD. But if you go back to the back of the screen, you see that all of these are sitting next to each other, and therefore these are adjacent, and therefore you don't have to write CD, C bar D. You can just directly write D. Okay, let's do a few examples with 4 variable maps. Okay, I'm just making up a few things and may or may not cover all the things we have talked about, but we try to cover enough examples, to do enough examples to cover everything. Okay, how about this? There are many implicants, so let's not worry about them. Let's start with prime implicants. This is a prime implicant. Let's go back to the previous one. This one is not a prime implicant. This one is not a prime implicant. That is because these two prime implicants are already covered by these two implicants are already covered by another implicant that covers them both completely. And therefore the two up and down are not prime implicant, but then D is a prime implicant. Okay? So, what do we do here? This is a prime implicant, so let's write it down. That's A, B bar. This is a prime implicant. Okay, I'm going to put commas here because I'm not sure if I want to order them all together eventually or not. So this is A bar D. There is another prime implicant. This one down here. And that one is A, C, D bar. Does anyone see any other prime implicant? And use a new color. That means yes, there is another prime implicant. Oh, in the middle of the ones, no. How about right and left? Okay. And this one is B bar D. How about now essential prime implicants? Okay. For essential, this orange one is essential because it at least has one or one mean term. Now I have two mean terms. This yellow one is essential. And this red one is essential. The only one that is not essential is the blue one. Let's write them down. The function is AB bar, because it's essential, ORed with A, C, D bar, ORed with A bar, D. Now let's see if the mean terms are covered. Okay. AB bar covers this, 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 and this. ACD bar covers this and this again. Remember, according to Boolean algebra, it's absolutely no problem covering one mean term 1 time, 2 times, 3 times, 4 times. And the orange one, A bar D, covers this, 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 this. I don't see any mean terms not covered. And therefore, this is the minimal realization of the function. And because I didn't have to go choose prime implicants, this is unique. Okay? Something I have to tell you, and that is KarnaughMAPs only give you two-level minimal realization. Okay? That means and, or. Later on we will show that they can also do or and. That's one thing. The other, if you want to go beyond that, if you want to reduce your function further into three-level network, you are on your own and back to Boolean algebra. Okay? Then you can play with the function as much as you want. But the good thing about two-level minimal realization is that two levels give you always the minimum delay in the circuit. If you go to three-level network, yes, you may save a few gates, but then three-level means more delay in the circuit. All right, give me a few seconds. That was a four-variable example. Let me do another example. This time, again, I want to do okay. Let's just add to what we already have. Okay. Let's do prime implicants. This is a prime implicant. This is a prime implicant. This is a prime implicant. And this is a prime implicant. Does anyone see any other prime implicant? Do you see any other prime implicant? So far I'm showing 4. Yes.
One of the third row down, and that's around.
The ones on the two sides. Yeah. Okay, good. So that's another prime implicant. So I have 1, 2, 3, 4, 5, right? Now let's do the essentials. Essentials are easy to identify. Just look at the minterms that have only one map crossing them. Okay, so and then the map that crosses them is the essential. So this is essential. So is this one. So is this one. Okay. First one becomes A bar D. The second one becomes A B bar. The third one becomes A C. And again, this covers all the minterms of my function, and therefore there are two prime implicants here, the horizontal orange one and the crossing blue one. These are not needed. Okay? All right. We can also have 5-variable maps. Okay. F, A, B, C, D, E. So we kind of kept extending our definition of adjacency, going from 2 variable to 3 variable to 4 variable. Now we have already got to 3-dimensional spherical. Okay, what do we do next? This is how I'm going to do it. I'm going to look at this as a 4-variable map where A is 0 and then the variables are B, C, D, E. This A is 1 and the variables are the same, B, C, D, E. Let's take this and this, this and this. The ones on the left are A bar, B, C bar, E. The two on the right are A, B, C bar, E. Boolean. Are they adjacent or not? They are. They are only different in A. What it means is I don't really need to include A and I can just write B, C bar, E. How about physical adjacent? Well, physical adjacencies are as far as you can even imagine. Probably not as far as you can imagine, but they're far. But look, if you look at the right-hand side map, as it being sitting on top of the left-hand side map, and if you look from above, what do you see? You see that the two on the right-hand side of the right map are sitting right on top of the two on the right side of the left-hand side map. Okay, so they are also adjacent physically. It's just you have to extend your imaginations. So look at these two maps as two spheres, one being on top of the other one. And therefore, these are adjacent. And I can directly write this. What are some other adjacencies here? These four are adjacent. So are these four, and they're all adjacent. So if you see something on the right and exactly the same thing on the left, okay, map them, drop the A. How about these? That's it. Has no equivalent on the right hand side, and therefore all there is to it is A bar, D bar, E. How about these two? Yes. Visualize the right map on top of the left map, and then look from the top. You are seeing that looking from the top, you see this first, and then right below that is sitting this one. Okay, therefore these are adjacent. All right. With all these adjacency definitions, let's do a relatively simple 5-variable map. Okay? 5-variable maps can get kind of messy. Before that, I go back and do the numbering. Especially for 5-variable maps, numbering is important because there are so many mean terms, and writing them, you don't want to write all the mean terms in form of product terms. You are much better off writing them in terms of the decimal numbers. Okay? 0, 1, 2, 3, 4, 5, 6, 7. You see these yellow numbers, or maybe I should use a different color, huh? Zero, 1, 2, 3, 4, 5. Sorry. Well, let's do a different map altogether. It's too crowded already. Just repairing my map, even though I don't need it. Okay, numbers. 0, 1, 2, 3, 4, 5, 6, 7. When you get to the third row, skip it, come back to it. When you get to the third column, skip it, and then come back to it. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 goes right here, 25, 26, 27, 28, 29, 30, and 31. Okay? So if I have a function with these mean terms, let's say, my function becomes sum of mean terms, 0, 1, 2, 5, 9, 10, 13, 21, 23, 27, or 26, 27, 29, and 31. Okay? Do you want to do minimal realization while we are at it? Why not? This is, let me see what other color I can use. Let's use this one. Prime implicant, prime implicant, prime implicant, like I said, when it gets to 5-variable maps, they get a little bit too busy sometime. This is a prime implicant. This is a prime implicant. This is a prime implicant. Yeah, it is getting there. So this is a prime implicant. This is a prime implicant. Okay. There's more. These two and these two, prime implicant. Okay. Now let's look for the essentials. Essentials are easy to identify. Okay, because of that, sorry, the map that encloses these four is essential. And this is also essential. Actually, that's it. These are my only two essentials. Okay, so let me clean up this space here and expand into this area. And do the minimal realization here. So I'm going to write the blue essential first, which is on the left-hand side. It's A bar. Okay. So my f of A, B, C, D, E is A bar. D bar, E. Okay. That is that, let me show you this. This is actually this. There is one more essential, and that's this one here. Okay, so let me write that. And I guess I'm also using blue for that. So that becomes A, C, E. Okay, the covered mean terms are the following. This, and this one already, and these four here. I don't have any other essential prime implicant, but I do have a good number of prime implicants that haven't been covered. And actually, this example really exercises our procedure here, because this procedure on the lower right hand side says what? It says find those prime implicants that cover the most number of uncovered mean terms. So let's exercise that in this new example. in this 5 variable example. And I'm going to use the orange one, okay, because there are 2 prime implicants that, two mean terms that is covering and not covered with anything else. And therefore, I'm going to write those. Ordered with A bar, A bar, B bar, C bar, and E. Okay. That done gives me this and this. Should be, thanks. And no D, right, okay. Do I still have uncovered mean terms? Yes, I do. I have 1 on the left map, 2 on the right map. Okay. I'm going to use the blue one on the right-hand side. And this one here. Okay. And that's going to cover another 2 new uncovered mean terms. And I'm going to use this color. It is not essential, but it is prime implicant. It is covering those 2 there, which is A, B, C bar, D. Then I am done with this and this. Do I have any other uncovered mean terms? Yes, I still have 1 uncovered mean term, and that has several options for it being covered. One option is that one, go here, this with this. Another option is this with this. I'm going to take the second option. I'm going to take this with this, which is drop A, it is B bar, B, C bar, D, E bar. Instead of that, I could do A bar, which is actually this. A bar, C bar, D, E bar. Either realization is good. But see, I started looking at my prime implicants with this one over here. If I had started looking, let's say, with this one, then the function would be it would be different with the same exact number of terms, but then it would be a different realization. In any case, that would also be minimal, and therefore we are saying that this minimal realization is not unique. Okay? Anytime your essentials are not enough to cover the function, then there is a good chance that your function is not unique. But there is also a chance that it is unique. All right, I'm going to zoom on this, let you look at it for a few seconds. And I think I did a good use of colors. And these are the original mean terms. This is the sum of standard sum of product representation of this function. Remember, standard sum of product representation. Instead of writing 5 variable product terms, I'm writing their decimal equivalent, okay, or mean term numbers. Then we look at that and we come up with the essentials and non-essential prime implicants, and we are including 2 essentials, okay, and then 1, 2, 3 non-essential or regular prime implicants to do the complete coverage of this function. All right. Yeah, the 5 variable maps, sometimes they start getting big, and so coming up with a good example is sometimes difficult, but having these colors and all that, it was helpful. I can also talk about 6 variable maps, but look at 6 variable maps like this. I'm not going to do any example, but look at it this way. Okay. Now, I've run out of spheres, and looking at the spheres one on top of each other. Visualize this however you want. Okay, but this is a 6 variable map, and if I have let's say something here and something here, these are adjacent. These 2 are also adjacent. Okay. But they only become adjacent if there is another 2 on this map here in the same place. For now, I have 2 prime implicants. Okay. 4 on the top 2 blocks and 4 on the left 2 blocks. All right, I just do this so that you exercise your understanding of prime implicants, essentials, and all of that. All right, we are done with the various types of Karnaugh maps and the implicants, prime implicants, and all of these. We have done some complete exercises, and because of the lost time and all of that, we have a few minutes to do a little bit more. Look, not all boxes in a Karnaugh map are necessarily defined. For example, if you have a system that tells you that, I'm trying to find a good color, your numbers A, B, C, D. You're designing a system. The system has A, B, C, D. And then it's doing something, turning some output on or off. But then the system says your input range is between, let's say, number 3 or greater than or equal to 3 and it's always less than or equal to 13. Okay? And then it says, if it is in this range, if the input is divisible by 5 or 3, the output is 1. I'm just making up a circuit. So this is the definition of the circuit. For inputs between 3 and 13, if input interpreted as a decimal number A, B, C, D is divisible by 3 or 5, output is 1. Okay? So, this is my W. I'm calling this one divisible by 3, 5. And then I'm writing the range of inputs 3, 13. Number 0, I'm going into the map now. Number 0, I don't really care. Why? Because it's not going to happen. I don't care what I produce for the output. I may produce a 0 or I may produce a 1. Do you care? Do you want to put a 0? Okay, I'm not going to put a 0 now. Number 1, I don't care. Number 2, I don't care. Number 3, yes, I do care and is divisible and therefore the output is 1. Number 4 is 0. Number 5, the output is 1. Number 6, the output is 1. Number 7, the output is 0. Number 8, the output is 0. Number 9, the output is 1. 10, the output is 0. 11, the output is 0. 12, the output is 1. 13, do whatever you want. Put a 0 or put a 1. Nobody cares. 14, oops. I don't care. 15, I don't care. Now I want to do a realization of this function. I can treat those that I said or don't care as zeros. If I treat them as zeros, this is what it becomes. If I treat them as zeros, it becomes 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0. That's if I treat them as zeros. If I treat them as zeros, then I have, in my mapping, I have this one standing by itself, this one standing by itself, this one standing by itself, this, and this. Not a very pretty picture. Okay, I'm not combining anything. So I don't like it. I don't like it as zeros. So let's treat them as ones. If I treat them as ones, 1, 1, 1, 1, 0, 1, 0, 1, 1, 1, 1, 1, 0, 1, 0, 0. It is better. Okay, see, but only for this example. Now that I have treated them all as ones, there are ones that help me come up with larger maps. But there may also be ones that are extra there, and I'm obliged to cover them. Okay? So I don't like that either. So I'm not going to treat them as ones. I'm not going to treat them as zeros either. I'm going to treat them as what is called don't cares. When I'm coming up with my prime implicants, I take don't cares into account. Okay, so here is a prime implicant. 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 But when I'm looking for my essential prime implicants, I only look for those prime implicants that have an actual midterm and not a don't care midterm. Okay, and therefore now I have this is essential because of the one I just put the asterisk next to. The vertical one on the left hand side, this one is essential because of this one. It's not essential because of this, because this is a don't care, and I don't care about the don't cares. Okay? And then, do I have any other essentials? Not only if I considered the actual ones and forgetting about the don't care. So don't cares help you give you better prime implicants. But when it comes to essential and covering them, you say, well, I've used them so far, it's good. I'm not going to continue using them from this point on. All right? So, this is what I'm going to do. This map is essential, and this becomes C bar D. Oh, by the way, this is also essential. This is essential, and this becomes AB. This is also essential, and this becomes A bar, B bar, and I still have one mean term not covered. See, this is covered. Well, let's not worry about the don't cares actually. So when I'm covering, I only mark the actual ones. So this is covered, this is covered, this is covered, this is covered. Don't cares, I don't care. And there is only one mean term not covered, and that can be covered by either including the B, C, D bar, or A bar, C, D bar. Okay, and that takes care of this one over here. Okay, takes care of this. So that's with the don't cares. So the functions can have either 0 or 1. And for inputs that we don't really care about their output, we just say these are don't cares. Don't cares only remain don't cares for as long as we haven't mapped them, right? Once you do a mapping, then don't cares become actual values, either 0 or 1. But see, you don't care about what they come out anyway. All right? But in mapping, leave them as don't cares. Don't decide immediately whether you want them 0 or not, because they can help you. Some can help you with being 0, some can help you with being 1. All right. I think that's good enough. And so this was lecture 5, and we are doing fine with the Karnaugh maps. We have actually covered everything there was to Karnaugh maps, and next we go on to some treatment of delays and some properties related to the transistor delays and everything. All right. We'll see you tomorrow, right?